So, all right, so we've seen that having this linear situation is not that great, because if we want to estimate the ATE, we still need to kind of impose, we need to pray that the true relationships are all linear, or that we have randomized data. But most of the time we don't have randomized data. So basically we're always here, right? This is the only relevant box. So when is the linear regression unbiased for the ATE? In general, like if you don't have a randomized trial, never, no way. So what do we do about that? So we need to adapt linear regression to somehow fit these nonlinear relationships. And the idea is to regress onto a combination of nonlinear functions. So instead of having your kind of vanilla linear regression where you say, let me assume that y is approximately some intercept plus some slope times x, forget about that. Let me kind of blow up x into different functions of x. So let's say x squared, let me say sine of x, and then I'm going to put coefficients in front of each of those functions of x, and then I'm going to fit those coefficients. So now this is much more flexible, because I can get sums of squares and sines and whatever. And you can think of this as like a mutate, right? So in this original case here, we just had a data set where we have y and we have x, right? And what I'm doing down here, and we're doing a linear regression, right? So what I'm doing here is I'm adding these other columns. So I'm adding a column x squared, and I'm adding a column sine of x, okay? And now I'm doing linear regression where all of these are predictors, okay? And by doing this, now I can fit functions that are more like wiggly, that have different shapes, where those shapes are determined by the shapes of these different functions that I include. And so, for example, if my true relationship were actually a sinusoid, right, then maybe I would get that this coefficient is 1 and these are 0, right? But if my true relationship really is a line, then I would get that this is 1 and that these are 0. So by including these different functions as predictors, I can more flexibly model different kinds of shapes without kind of committing to one or the other. So generally, we call these basis functions, and you can write it like this. So what I have here is a sum over different basis functions. So here, like, again, if I were thinking in terms of my little data frame, I would have x, I could have b1 of x, I could have b2 of x. So b1 and b2 are different functions that I could pick, like sine or squared or whatever. And then I have a sum of some coefficient times this plus coefficient times that, so on and so forth, to predict what y is. So this is the idea of a basis function expansion. That's what we call this. So let's just look at that in practice. So we have some data here. So these data, obviously the relationship is not linear, right? So if we fit linear regression, this is actually the fit that we get. And I'm showing you here the kind of, this is the model. This is a statistical model in the sense that it's like a set of candidate functions, right? So it's all that I can play with beta 1 and with beta x. Those are my little knobs, right? And I'm saying all the functions that are possible are those that are beta 1 plus x times beta x. And the best one of all of them is this line here, which just looking at it, it sucks, right? So can we do a bit better? Well, let's add in these extra basis functions. So let's add in x squared and x cubed as basis functions. And the way I'm going to do this is by having, first, you can read this inside out. So first I'm going to have my data, and I'm going to mutate it to add these new columns. So x2 is x squared, and x3 I'm saying is x cubed. And then I'm going to add x2 and x3 as predictors when I do my linear model fit. And this is what I get. So an improvement, definitely an improvement. So what it's decided here is that, like, okay, basically this looks more like a parabola than a line. And so if you actually look at and I think the code for this is also here. Yeah, okay. So you can see here what my data generating process is and how I made this. So you can play around with this at home if you want. If you actually look at the coefficients from this fit on these data, you'll see that you maybe have like maybe like a 2 or a 1 here, and then some kind of smaller number here and a smaller number here. So it's saying like these data look more like a parabola, less like cube, less like a line, and that's how you're kind of getting this overall fit. But now you can actually do that a little bit more easily than doing the explicit mutate. You can LM actually with this formula interface can kind of do the mutate internally, and the way you do that is you just put x squared and x cubed, and for some reason you have to put this little I around those terms to say no, like I literally want x squared. If you don't do that, it doesn't work. It's just a choice in terms of the syntax, how they decided to do it. There's no really good reason for that. You just have to kind of know it. And you're welcome to kind of read up more about that and explain it to me if you want. I don't really know why exactly you need that. But this is how you do it. And this is equivalent, right? So this is exactly the same. I ran these two codes and they gave me the same result. It's just a kind of nicer way to do it, so you don't have to do the explicit mutates. And it gets better, right? I'll show you what I mean. So let's do something even more complicated, which is I'm going to choose a basis function that is x times an indicator of x being greater than 0, and another basis function that is x times an indicator of x being less than 0. So what do those look like just by themselves? So we know, like on this previous slide, that x, so let's just draw a plot here. So this basis function x just looks like this, right? This is x and y. And this coefficient lets us kind of control the slope of the line. So if that coefficient is more or less, it controls the slope. Beta 1, this is also actually a basis function, which is the constant, right? So changing beta 1 lets us add or subtract to that constant, shift that up and down, and then we're adding those two together to get our final fit. And then we're also adding this thing here. What does that look like? This is a parabola. It looks like that. And what is this? A factor times a parabola. It actually kind of controls how like wide it is. So by changing this, I can make fatter or like narrower parabolas. And then similarly over here, I have this basis function, which is this like cube, kind of looks like this. And similarly, by changing the coefficient, like a larger coefficient makes that kind of wider, and or vice versa. Bigger coefficient makes it narrower, larger coefficient makes it wider. And then I'm just summing all of those together to get this final fit. Okay, so that's the idea for the coefficients. So here, what do these basis functions look like? Okay, so this one, like x times this indicator, well, let's just look at the indicator first. So we know that the indicator looks like this. So it's 0, and then it goes to 1, right? That's the indicator. And then what does x times that look like? Well, the function y equals x looks like this, right? So if I multiply them together, what I'm going to get is a function that over here is 0, right? Because it's 0 times, I don't care what this is, it's always going to be 0. But over here, it's going to be 1 times whatever this is, which is going to be whatever this is. So this x times this indicator is a function that looks like this. So it's flat, and then it starts going up like that. So this is called a hinge function for obvious reasons. It kind of looks like a little hinge. And also, it's you may have seen it referred to as ReLU, also rectified linear unit. This is from the neural network world. This is actually a very important function in how you kind of stack neural networks together. But anyways, that is the basis that we're using here. And what about this one? This is a similar kind of thing, except let's try it over here. So here we have the indicator is it's 1 over here and then 0 over there, and then we have x. So this hinge looks like this. So we have like that, and then flat over here. And so if we multiply this by different coefficients, what we can get is we can change, this part is always 0, but we can change kind of the slope of what it is over here. So we can get different it really is like a hinge, right? By varying this beta, so this part is always fixed at 0, but we can make this other part kind of flop around and go either up or down or whatever direction. So that's really what we're playing with. And then we're adding these together, right? That's what this sum is. And we're also finally adding some constant, which can shift the whole thing up or down. So really what we're able to fit since it's 0 here and 0 here, what we're able to fit is like a kind of V that we can shift up or down with a constant. So either a V or like it'll basically just have like one point at which it can like flop up or down, and then we can move that point up. And so by doing that, we actually end up with this fit here, right? Which is pretty good, pretty good. And all of this is just linear regression, really. Like linear regression doesn't, the regression part doesn't know about like, it's not doing anything special with these basis functions. It's just doing gradient descent to find beta 1, beta 2, beta 3, right? You can, like, it doesn't you just did a mutate, right? You just did a mutate on your original data to create these like constructed predictors. And then you're just doing linear regression on top of those constructed predictors. But by doing that, you can actually get nonlinear functions. So it's really quite clever way to get a linear regression to fit a nonlinear function. And the last thing that I want to say about this slide is that this kind of slightly complicated thing we can do really easily in R if you use the I is also how you get an indicator function. So I want to say indicator of x greater than 0. And then if I do x colon that, that means I want the product of x times the dummy where this is 1 plus the product of x in the dummy where this is 0, which is where it's 1. It basically just says greater than versus less than and treats those as two different things. So that little colon gives you that kind of a product of those two, this product and then also that product. So it's just a cute little syntax. And you can play with model.matrix. Again, I encourage you to do that. Make this data set, do model.matrix with just the tilde x colon I x greater than 0, and you'll see what comes out and how it works. First, I mean, maybe even first, before you do the x colon, just do the I x greater than 0, and then add the x colon and see what comes out. And do it with like, just 10 rows or something like that, so you can see clearly. All right, so we're doing better. Can we do even better than that? Yeah. So there's this thing called a spline, and a spline is basically just something like this. So it's x times indicators. But instead of typing it out like this, you can get R to do it automatically for you with this BS function, stands for B-spline, and it's in the spline library. And what I'm doing here, when I say df equals 3, it's like saying I want 3 hinge points. So here I have 1, which is x is greater than 0, x is less than 0. But I could also add here like an x is greater than 1 and x is less than 1, and then I would have like a hinge here, and then potentially also a hinge over there where I could kind of like flop this line. And so df is basically saying like how many of those hinge points do you want? Degree equals 1 means that the product with these indicators is an x. So it's going to be like a line connecting these little hinge points. So if I had an x squared, instead of getting a hinge function that looks like this, I could have gotten one that looks like it'd be 0 up until here, and then after here it turns into a parabola, right? So I could have like, I could connect little like parabolic segments together instead of little line segments together and get something kind of flexible. So that I'll show you what that looks like. But that's basically what degree does. So degree here, degree equals 1, means I'm connecting line segments together. If I had degree equals 2, I would be connecting little parabola segments together so I could get little curves. And again, df just means like how many little like hinge points do I use. But all of that, you don't have to think about constructing it manually. You can just do it automatically with BS. And again, if you do BS inside model.matrix, or even by itself, if you have like data $x, you can see all of the different like predictors that it'll spit out this like big matrix with like a bunch of different columns. that it constructed in this manner. So here's a case where I let the number of hinge points be 10, and again I'm kind of connecting linearly, and I'm fitting, and again it's amazing, right? This is really just linear regression where I made like 10 or 11 different predictors using this thing, right? I've just constructed those, and then I've like glued them together in this very clever way that gives me this nonlinear fit, even though I'm actually just doing linear regression. And here I'm connecting polynomials of degree 4 instead of lines, and you can see I actually get some nice curves instead of these like more jagged fits. So that's splines. You can get some very like rough fits. And then you can actually get very, very close to all sorts of very complex things by doing high complexity splines. And you can do this with 2D data as well. So for example, here's main terms linear regression. We were talking about this before with the interaction term. That's what I'm going to show you here. So this is just a 2D fit. So I have a slope for x and I have a slope for a. And here that slope for a is actually represented by like the difference between these two lines, which you can think of like, again, I'm looking into like a two-dimensional, like a is another axis. A is kind of coming out at me. And like the pink points are closer and the gray points are further away, or vice versa, however you want to think of it. And so there's actually kind of like a slope that's coming in this surface between a equals 0 and a equals 1. That's one way of kind of visualizing it. So I can just kind of flatten that and use the color to tell me what's closer, what's further. So this is the fit that I get. Cool. But what if I want obviously this is not that great, right? Because if you look at the gray points here, it really kind of looks more like, at least to the naked eye, that maybe the gray line should kind of look like this, and then the pink line should kind of look like that, right? That's what it looks like to me. But because this model is very constrained, that there's only one slope for x, no matter what a is, a equals 1, a equals 0, the slope for x is going to be the same. So it can't do that. But we can let it do that if we put in what's called an interaction term. So here, now my model is this. So now I have a times x, beta 3. So if you imagine the reason this results in like allowing for two different slopes is that you have when, so say imagine a equals 1. So if a equals 1, then what you get is beta 1 plus, just call it beta 0, sorry, plus x beta 1 plus, this is beta 2, because it's times 1, plus, and then here I'm going to do a equals 0. And then a equals 1, so it's x beta 3. And that is equal to, so I'm just going to combine the beta 0 plus beta 2 plus x times beta 1 plus beta 3. Whereas if a equals 0, I have beta 0 plus x beta 1 plus, this is 0, that goes away, that's 0, that goes away. So that's it. So you can see that this line, my intercept is different than this intercept, and this line gives me a different slope. So that's what I have here, right? That's what you're seeing. By adding this interaction term, I've allowed for different slopes and intercepts across the levels of a equals 1 to 0. Basically, that's what these two parameters do, is they say how much different is the slope and the intercept from a equals 1 to a equals 0. So you can do that with this interaction term. And okay, so let's go back to our insurance data set here. It says use vanilla, what we call main terms, linear regression to predict the charges from all of the variables. We already did that. And report the root mean squared error. And then add interactions and basis functions to try to get predictions with lower RMSE. All right. So we can start here. We already did this part. Okay, so this is my main terms regression. How do we get the mean squared error? We can get the predictions on our data. And well, let's just start with, let's do it like this. Doesn't really matter how you do it, but I think this this is kind of clear. So here's y hat, and then I want to get the mean of y hat minus what charges. So maybe even, let's just say call it predicted charges. Okay. Oh. It'd be helpful if I call the right function. Oh, and I need to do squared, sorry. Okay, so this is the mean squared error, and let's just take the square root of that. So we have root mean squared error. Okay, so this tells us that we're off in general with this main terms regression. We're off by about $6,000 on average for any, you give me a random person, tell me, I'll give you the prediction for what their charges will be this year. You give me their true charges, I'm off usually by about $6,000. That's what this says. Okay, so now let's add interactions and basis functions, and we can try to get something a bit better. So let's say that I think that maybe there's an interaction between whether you're a smoker and age. So the slope for age is different whether or not you're a smoker. So let's let it work like that. So I can now look at, I'll show you what that did. So now you can see that there is one slope for age, and this is effectively the slope for age for if you're not a smoker, and this is the slope for age if you are a smoker. That's effectively what how you can kind of like read this. Now again, do those things mean things causally? No, probably not. But because that requires a lot of assumptions in order to make that interpretation. But here we're just looking at the the value of the coefficient without ascribing necessarily any meaning. It was just this is the estimated slope. That's it. So I've added that. I can also add, maybe I want age, instead of age to be a line, I want that to be some kind of spline. So let's just put I don't know, df equals 4. So I want kind of like 4 hinge points, and maybe I want to connect them with like little parabolic segments, or something like that. Sorry. So now what do we get? We have so this spline thing actually outputs these like 3 different or 4 different basis functions, right? Because we're actually have these 4 little functions that are being connected at these different hinge points. And then we're interacting those. We're saying that what the coefficients on those are different for if you're a smoker or you're not a smoker. So you get the ones for if you are a smoker, and then you should also, here we go. These are the values for the coefficients if you are not a smoker. So now, I mean, interpreting those gets even harder, right? Like, what the heck does that mean? But it doesn't matter because we're not interested in those coefficients, right? Let's say that, right? Because like if we're predicting the ATE, it doesn't matter how complicated all of this crap gets, right? We can still just use the plugin. So we can still just say like, okay, this is our fit. It's complicated. There's all these coefficients, but we don't care what those coefficients are, right? If we have the proper assumptions, again, here maybe we don't, but if we did, we would still just be doing something like this. We would be doing insurance, and then we mutate. So let's say what's the effect of smoking on charges. So we would just get the predictions, assuming everyone's a smoker. And then we're just going to ignore that error for a second. And then the predictions were nobody's a smoker. Bam. So in this case, having this kind of more complicated model, it didn't really change that estimate. It's still saying that there's about $24,000 difference. But I think this is very important to understand, right? That we can use a very complicated regression model here, and it doesn't matter. It doesn't matter that there's no one coefficient, right? So here at smoker, yes. Actually, so you can see actually the coefficient for smoker is only like $23,000, right? But when we do the plugin estimate, it's like 24, right? So that this one coefficient by itself doesn't mean anything. What means something is the difference between the average predictions of these models, no matter how complicated that prediction model actually is. And in this case, it's pretty damn complicated already, right? Even though it's just a linear model, we've included all of these like spline bases. And so it can actually get very, very complicated. And why would we want this to be more complicated? Well, because it fits the data better. So for example, we saw that if we just had the main terms model, we had like what was the average prediction error was like $6,000 or something like that. Yeah, $6,041. I don't know, let's just see how much better we do by including this interaction and these splines. I don't know, maybe it's not too much better, but let's see. Okay, so now we're getting an error that's under $6,000. Okay, which yeah, it's pretty wild. And actually, I'm not 100% sure why this error is happening or this warning is happening here, because this should be fine. So normally when you see this, it's because you have more predictors than you have data points, which I haven't really talked about. But basically, in that case, you don't have a unique solution. And so you need in terms of like, there are multiple functions. You have so many functions that there are multiple functions that fit equally well, if that makes sense. And so it doesn't know how to pick one among all of those. That's effectively what this means. And that normally happens when you have more predictors than you have data points. But in this case, we shouldn't have that. So I'm not totally sure why that is happening. Maybe if I use this little colon or something instead. No, same thing. But anyways, yeah. So this is kind of cool. I'm just showing you how it can actually get quite complicated, but it doesn't matter. This is still the same. And if you make your model more complex like this, you can get lower mean squared error. You're getting better predictions. You're fitting the data better. That's good usually. So there is a point at which you can fit your data too well. But with like linear models, usually your problem is that you're underfitting. There's a lot more. I mean, now I'll say this, like, you're kind of already understanding this. You're like 80% of the way to like full on machine learning stuff, which is great. That's where actually you want to be. And I want to say, like, this is kind of the beginning of your journey, not the end, hopefully. So you're getting very, very, very close to doing super sophisticated stuff already. And there's more to learn, but this is a good start. So fitting the data better is a good thing. So here's an example, right? Here you had here we have a data set that has some confounding and has nonlinear relationships. No problem, right? So here I'm fitting my one covariate. I put a spline on it, and I have an interaction with the treatment, and boom, I can fit this really well, even though over here and over here, right, we have, over in this region, we have very few red points, and in this region, we have very few gray points. So there's like a little bit of like extrapolation going on, but it's extrapolating correctly, more or less, because it has been able to kind of capture the true pattern, the true functional form of these data. And so I can actually get the treatment effect without bias, whereas if I had just used linear functions and not included the interaction, I would have done a poor job at estimating. So basically, by if we go way back up here, remember, we need to do a good job estimating and a good job identifying. So we have identifying assumptions, yes or no, great. But then if we do a bad job estimating, it doesn't matter that we measured all our confounders, because you just fucked it up. You need to do both. So there's no point in doing a great job collecting data and thinking very carefully about your assumptions if you then are going to do a very crappy job at actually estimating that thing, or even worse, at just picking a random coefficient and saying that represents a causal estimate, or even, you know, some observable estimate. Like the coefficient may not mean anything. So that you need to be doing this kind of plugin thing. Think about that. Think about the plugin philosophy, and think about how you can estimate the conditional means flexibly and well, so that they actually represent the true conditional means. And then you end up in this kind of happy world, assuming your causal assumptions are met. And it's okay if they're not, right? That's something that you talk about in your discussion. But at a minimum, you want to get as close as possible to estimating the observable ATE, because even if that's not the true ATE, you can't identify it because there's missing confounders or whatever. At least then you've broken up the problem, right? At least then you said, well, the only thing that's missing here is being able to measure these confounders, and I can talk about that. I can think about that clearly. I can say, here's if I had this other variable, here's how I think that might change the answer, right? And people can debate that in a transparent way. Everyone knows what we're talking about. Whereas if you're stuck over here, you know, saying that you have this coefficient, you know, if you include another variable in your model, that coefficient changes. What does that mean? Who knows? It's completely meaningless. So that's why we want to be in this world where even if it's not perfect, we at least know what the hell we're talking about. So I'm going to end it there. It's been a kind of a long lecture. Hopefully we can edit it down to reasonable time. But hopefully this has been interesting and thought-provoking for you, and I will see you next week.